Hello, today we study Newton's method and we use this method to approximate a zero of a function. So suppose that you have some equation f of x equal to 0 and you want to find zero or solution of this equation. And you know most of the time we cannot solve the equation exactly. If you remember, when we have quadratic equation, right, we know the formula. But when the degree of the polynomial is bigger than 3, we don't have any general method to solve that, right? So we need to approximate the solution. And that is the main purpose of today's video. Okay? Remember that we learned the intermediate value theorem. That theorem says if your function f is continuous on some interval a and b and f of a times f of b less than 0, then the equation fx equal to 0 has at least a solution on that interval, right? So what does it mean fa times fb less than 0? That means one of the points afab or bfb should be above and another one is under the x-axis. So I may assume that a is right here, and I may assume f of a is less than 0, and you have f of b in here. F of b is bigger than 0. Since the function is continuous, the graph of this function is continuous. Then when you connect, somehow, right? When you connect, you go from this point to this point. Now you should intersect with the x-axis at some point. And that is the solution of the equation fx equal to 0. It is the intermediate value theorem. This theorem tells you about the existence of the solution, right? So let's emphasize this. On some interval. All right, now suppose that we know that the equation has solution and we need to find that solution. And we suppose that the function is pretty good, like this picture. So the function is differentiable. Let me write it down. And you suppose that f is differentiable. Means the graph of this function has tangent line at any point on the considered interval, right? Then we may use the following method to approximate the solution if we cannot solve that. Okay, let's approximate. Look at this. I may start from A. How about this? Let me start from A. I will find the tangent line at A. The tangent line to the graph at A. So I have this tangent line. We know how to solve this problem, right? If you have a point, if you have function, you may differentiate that and you can write a tangent line at A. I can write this right here. Tangent line at A, FA. So that is what? That is y minus f of a, right? Equal to f derivative at a times x minus a. Is that correct? Then, as we have seen in the picture, this tangent line will intersect with the x-axis at some point. Okay, let me denote by x1. Right? I denote this by x1, so let's denote a by just x0. That is the first point. Okay, then at this point, so I have the corresponding point on the graph of the function. It is right here. From here, I will do almost the same thing. I will make a tangent line, to the graph of the function. Okay, I'll make a tangent line here And this tangent line again intersect with the x-axis at some point. So let's say this is x2. Okay, this is x2. And you see each time, we start from x0 in here, we move to x1, and then we move to x2. And x2 is closer to the solution than x0 and x1. Is that correct? And you just repeat this process. You get a sequence of numbers x0, x1, x2, x3, and so on. And that sequence converts to the solution right here. So that is the tangent line method or Newton's method. Okay, let me continue this, right? I need to find the tangent line at A, and then I will find the intersection. I'll find x1. Okay, let's find x1. Let's find x1. In order to find x1, we just put y equal to 0, right? Means, put y equal to 0 and plug this into the equation of the tangent line. So I have, in this case, I have negative fa equal to f derivative a x minus a. And then you have x minus a equal to negative fa divided by f derivative of a. Or you can write x equal to negative fa divided by f derivative of a, and then plus a. Or you can write, that is a minus fa divided by f derivative of a. And as we have seen, we denote, right? We denote a is x0. Then the intersection, x1 should be x0 minus f x0 divided by f derivative at x0. So if you do one more iteration, right? Does that make sense? So you do one more iteration. So you want to find x2. You do almost the same thing. And you just need to replace x1, x0, by x2 and x1. So I have x2 equal to x1 minus fx1 divided by f derivative at x1. The function is differentiable at any point on the interval. So, everything is good in here. And then, in the end iteration, you might have the following one. Xn equal to xn minus 1 minus f of xn minus 1 divided by f derivative of xn minus 1. You see? And of course, in this case, xn is closer to the solution, right? When just n increasing. That's how we can approximate the solution. Does that make sense? All right, so this is the general formula of the Newton method. Okay, general formula of the Newton method. And of course, we suppose that the function is differentiable on the whole interval a and b. Okay, don't forget that. Let's consider the following example. We need to calculate 3 iterations of Newton's method to approximate a zero of the function x cubed minus 2x plus 4. And let's use the initial point x0 equal to 1. Okay, let's say that is x0. So firstly, I need to prove that this polynomial has 1 0. Okay, so we can use intermediate value theorem. It's about the existence, right? So in order to use intermediate value theorem, I need to pick 2 points, right? Such that f of 2 endpoints has product, has negative product. So the easiest point is 0, right? So you pick x0, then f of 0 is 4, which is positive. Perfect. You need to pick another point such that the function is negative. Agree? So I think you may pick a good number enough, right? For example, negative 3, right? When you pick x equal to negative 3, f of negative 3 is equal to negative 27 plus 6 plus 4, and that is negative 17, less than 0. So by the intermediate value theorem, f of x has 1, 0 on negative 3 and 0. All right, now we need to approximate that, and we start from 1. Okay, so after the existence, we need to approximate. I will use the formula xn equal to xn minus 1 minus f of xn minus 1 divided by f derivative of xn minus 1. Our function is good because this is polynomial, right? And since any polynomial is differentiable, so we are good to apply the Newton's method. And this is the formula we just worked out, right, previously. So now I just need to calculate, right, x1, x2, and x3, because they ask us to find 3 iterations. Okay, so let's do this. X1 is x0 minus f of x0 divided by derivative of x0. Let's find the derivative, right? We need that anyway. F derivative equal to 3x squared minus 2. Okay, so you plug 1, right? x0 is 1 into the derivative and into the function. I have, let me write here, f1 is 1 minus 2 plus 4 is 3. F derivative at 1 is 1. Then x2 equal to x1 is 1 minus fx is 3 over 1 equal to negative 2. Do you see something interesting in here? We start from 1. We show that the equation or the function has at least 1 0 on negative 3 and 0. But we start from 1, which is not in this interval. But after one iteration, we already move in that interval. You see that? So now we are in the interval. Even, we don't see the picture like this, right? We don't see the picture like this. Does that make sense? So that is also interesting, right? All right. Now let's move to the second iteration. That is the first one. Oh no, I think this should be x1. Okay, so let's move to x2. x2 is equal to x1 minus f of x1 divided by f derivative of x1, and x1 is negative 2. So I have f of negative 2 equal to negative 2 cubed minus 2 times negative 2 plus 4, that is 8a plus a is 0. Okay, so interesting. So we already get x1, x2 equal to x1, and if you continue, so you get almost the same point. Is that correct? Because this term is already 0. So what happened in this situation? Interesting. Oh, the thing is, negative 2 is already your solution. So that's why when you plug, when you stop at negative 2, so you are done because you don't move, and you already arrived that point. You see, when you arrive this point, so you don't need to do anything else. Is that correct? So that is our situation in here, right? That is our situation in here, because you plug -2 into the function and you get 0. So this term is 0. That means x2 is x1. So you continue that, you get x3 is x1 and just equal to -2, because this is already solution. Okay, let's choose another problem. Let's solve one more example. So now let's pick the function 2x cubed plus x squared minus x plus 1. And we start from, let's say, x equal to 1. Okay, x0 is 1. Again, I need to show that the polynomial has at least one 0. Let's find it out. I pick f0, I get 1. So I need to choose another point such that the f of x is less than 0. From this example, I think I just need to pick -2, I guess. F to -2 equal to 2 to -2 cubed plus -2 square minus -2 plus 1. So I have -8 times 2 plus 4 plus 2 plus 1. 16 minus 7 is -9, less than 0. Perfect. So we want to approximate the solution on -2 and 0, right? At least one solution, or 1 0, whatever, right? Okay, now let's start from 1, and let's use previous formula. I have x0 equal to 1. Then x1 is x0 minus f of x0 divided by f derivative of x0. So we need to find the derivative, where f of 1 is 2 plus 1 minus 1 plus 1 is 3. And f derivative of x is 6x squared plus 2x minus 1. Then you can find the derivative at 1 is 6 plus 2 minus 1 is 7. You see? Then you have x1 is equal to 1 minus 3 over 7, which is 7 over 3. So I have 4 sevens. Agree? So it is closer already, to the interval, right? You see, from 1 in here, you move to 4 over 7. And our interval is 0 and -2. So our solution should be around here. All right, let's do one more iteration. So you have, that is your x1. Let's move to x2. x2 is x1 minus f of x1 and divide by derivative of x1. Okay. So you have 4 over 7. What is f of 4 over 7? So I need to plug 4 over 7 into the function, right? My function is 4 over 7 cubed plus 4 over 7 square minus 4 over 7 plus 1. Okay, that is my function value, and the derivative is 6 times 4 over 7 square plus 2 times 4 over 7 minus 1. Okay, let's find this out. So the function value at 4 over 7 is 1.128, and then the derivative at 4 over 7 is 2.102, and you plug these numbers into this formula, then you get what you need, right? So in here I can write f is 1.128 divided by 2.102, and then approximately equal to 0.035, and you can see 0.035 is already closer to 0, right, than 4 over 7. It's somewhere right here. So that is just second iteration. Okay, and then you do almost the same thing. If you move to one more iteration, you want to find x3, so you need to find the function value at that point and then the derivative at that point, and you plug all this number into the formula to find x3. So please do that yourself, and then if you want, you go ahead to find x4, x5. Okay, and don't forget that when you increase the n, right, so you have a sequence x0, x1, x2, and so on, xn, and so on. And this sequence converts to the solution x star. Okay, so if you want, when you increase n, you get more exact approximation. Okay, now let's show one example, when this method does not work. So you might consider the following example. The function y equal to cube root of x. And we know that the function has 1, 0, x equal to 0, right? But the bad thing about this function is the function is not differentiable at 0. Does it make sense? Not differentiable at 0, because the derivative of this function is what? The derivative is 1/3 x2 negative 1/3, or 1/3 minus 1. That is 1/3 x2 negative 2/3. Or you can write that is 1/3 cube root of x squared. The derivative is not defined at 0, and of course the function is not differentiable at 0. So in that case, if you apply the Newton's method, you have the following. So I may use, for example, x0 is 0.1. Okay, then you have x1 is what? x1 is x0 minus f of x0 divided by f derivative of x0, right? So that is 0.1 minus cube root of 0.1 divided by, in this case you have divided by 1 over cube root of 0.1 square. Or let's say this, in general, right, we have xn plus 1 is xn minus f of xn divided by f derivative of xn. We'll see what happens with this function. As xn is xn, fxn is cube root of xn, right? And if you say you divide by the derivative at xn, so you have 1/3 cube root of xn square. So if you simplify this part, you get the following one. You get xn minus 3 cube root of xn times cube root of xn square. Is that correct? Because you divide by a fraction, so you multiply by the inverse, right? You flip this to the top. So you have xn minus 3xn, which is negative 2xn. Even you don't need to find x1, x2, x3, but in general, you have xn plus 1 equal to negative 2xn. Okay, so what happened? You use a recursive relation to find the next one. So you have negative 2 times xn is negative 2 of what? Of xn minus 1. Is that correct? Because if you apply the same formula for n, right? So you just go back from xn to xn minus 1, and here multiply by negative 2. Then I have this is equal to negative 2 square xn minus 1. And then you continue this, you get negative 2 square times negative 2 xn minus 2. And so on. Does that make sense? So overall, you get negative 2. Let's say, let me write cube in here and xn minus 2. N equal to if you pay attention, the power of in here is 3, and then when you when you add 3 with n minus 2, you should get n plus 1. So if I settle down to x0, right? If I settle at at x0, so here I should have -2 to the n plus 1 times x0. So that is my xn plus 1. Okay, and that is what? That is -2 to the n plus 1 times 0.1. This sequence does not converge to any point. Does not converge to any point. Okay, so you can see that obviously, like you might pick n. You might pick even n's, right? Or you might pick odd n. When n is even, this value is just -2 times 0.1 is 0.2, -0.2. But when n is odd, so n plus 1 is even, so you get 2 times 0.1, which is 0.2. So this sequence is very strange, right? That is just 2 points, right? From negative 0.2 and 0.2. You see that? And they just change from this to this, and then from this to this, from this to this, from this to this, and the sequence never converges to any point. So in this situation, you cannot apply the Newton's method, because your function is not really good. Your function is not differentiable at this point. Does that make sense? So I think that I finished my video in here. That is just very brief introduction to Newton method. And if I give you such problem on the quiz or test, probably I just give you a very good function that you can differentiate, and then you can find x1, x2, x3, the first iterations. I think that is it. All right. So if you have any questions, please feel free to let me know.